right, so this is Mr. Boone here. I know that you guys are off for the next week and a half until Thanksgiving because of all of the fires. So sorry to those of you who have been affected by the fires. I realize many of you have had to evacuate where you've been living. And so as a result, we don't have class. And so I'm going to post a video today and probably another maybe one or two over the next week or so where we can talk about the topics that we would be talking about in class. So last time we talked about nested quantifiers. We also talked about how you can have various sets to deal with. And when we talked about numbers a bit, there were three big sets that we mentioned, which were the natural numbers, the integers, and the real numbers. All right? There were a couple other ones, the whole numbers, as well as the rational numbers, but we're not going to be really dealing with those as our given sets today, so we'll just look at these three. And we called them N, Z, and R. Those are the typical mathematical notations. And so one of the great things about nested quantifiers is that you can write a lot of mathematical definitions using them. All right? I should probably close this door. So let's just look at a few common words that we've used before. So even number, odd number, rational number, and prime number. All right, so you guys should all have a good idea of what these words mean. And so let's just go through these one by one and how we could define them using the quantifiers that we have. And so the first one is even number. Then we're going to do odd number, which will be very similar to it. And so when we're talking about even numbers, so among these three sets, which set are you going to use when you're talking about numbers that are even versus numbers that are odd? Yeah.
Integers?
Yeah, we're going to talk about the integers. Because negative numbers can also be even or odd as well. You could talk about just the natural numbers, but certainly you're not going to be dealing with the real numbers. Like if you have a fraction like 3/5, you're not going to talk about that being even or odd. Or if you have something like pi, that's not going to be even or odd. All right, so we're going to want to deal with. So we have for all x in the set of integers. And we are going to say that x is even. And so we are going to need to say what conditions something would have to be in order to be even. And so we do an if and only if because we want to, whatever conditions that we write over here, we want that to cover all the even numbers and only the even numbers. All right. So what does it mean for an integer to be even?
Yeah. It ends in 0, 2, 4, 6, or 8.
So you could, when we talk about base 10 representation, that's what it would be. So there's a few different ways that we can talk about whether a number is even or not. All right. So one way that we can do so is that you could say you could divide a number by 2, right? It's divisible by 2. And you can divide any number by 2 in a sense. For instance, 1 divided by 2 is a half. But what's special about when you divide an even number by 2? What do you get?
Your answer's an integer?
Yeah, so you end up getting an integer when you divide by 2. So one way of saying it is like this. You could say that x is even. If x is even, then x divided by 2 is an integer. And the arrow goes in both directions. If x divided by 2 is an integer, then x is even. All right, so it's an if and only if, because all even numbers, you can divide them by 2 and get an integer. And if there's a number that you can divide by 2 and get an integer, then that number's even. So that's one way that we could describe it. It's not the way that mathematicians usually define it, but it is one way to define it. So another way that you can think about it is you can sort of do a little work off to the side and think about x over 2 is equal to some integer y. All right? And that would mean that x is equal to 2 multiplied by y, where y is an integer. All right? And so the way that mathematicians actually prefer to write the definition of an even number. So it's something that you can describe about integers. Make it a bracket actually, just to make it a little bit more clear as to where these go. And so let's look at this. So x is even. If x is even, then there exists some number y in the set of integers. So some new number y. If x happens to be 0, it'll be the same number. But there is some other number out there in the integers that x is equal to 2 multiplied by that number. All right, so you could think about it. If x is even, so maybe x is 10, 10's an even number, then there exists y such that x equals 2 times y. In that case, y would be equal to 5. Or if x is equal to 16, then y is going to be equal to 8. But if x wasn't even, maybe x is equal to 15, well then such a y isn't going to exist. All right? If x is equal to 15, then there exists y such that x is 2y is going to be false. Because the only such y that exists would be 7.5, and 7.5 is not an integer. Does that make sense?
Right, so you mean the y, there exists a y that is a member of the integers.
Yes, yeah.
For which
so
x
that's
equals
what this
2y. Right.
notation here means, is that y has to be a member of the integers. And y can be different for each value of x. So notice that because we've nested the quantifiers, you start by saying that for every x, some y exists. The y can be different depending on what the x is. All right?
Okay.
So now let's look at an odd number. And so let's look at sort of our definition here. So x is even if and only if there exists a y such that x is equal to 2y. So you could just say that a number is odd if it's not even. And then you could say that there doesn't exist something. Although usually in mathematics it would be more useful to define it away in such that something exists. All right. So for an even number, we have x is equal to 2 times y. For an odd number, well, you couldn't have x as 2 times y. Any idea of what it could be? So you think of a similar equation that would always work for an odd number.
X equals 2 times y plus 1.
Yep, very good. So you could have that x is equal to 2 times y plus 1. So if y is an integer, then 2y plus 1 is an odd integer. All right? So we could say there exists y in the set of integers such that x is equal to 2y plus 1. All right? And so say that x is 15. Well, then y would be 7 because 2 times 7 plus 1 is equal to 15. Or say that x is negative 65. Well, then y could be negative 33 because negative 33 times 2 is negative 66. You add 1 to that, you get negative 65. And so, regardless of what x is, as long as x is an odd number, you'll always be able to find some other integer that you multiply it by 2 and add 1, and you get that same odd number. All right?
Okay.
So now, let's look at the next one. We want to talk about rational numbers. So now, instead of looking at things that are integers, we want to look at things that are real numbers. And so, because every real number can either be rational or it can be irrational. So, does anyone remember what our definition for a rational number is?
It's any number that can be expressed as a over b, a divided by b, when a and b are both integers.
Yep, very good. So x is rational. We would want to have that x equals a over b, where a is an integer and b is also an integer.
But isn't there something about 0?
So you can't divide by 0. That is correct. And so you could say that b is an integer and that b is not equal to 0. All right? So let's look at this then. All right? So for all x in the real numbers, x is rational. All right? And so a rational number is one that, so now there's two different things that have to exist, right? And we just need to exist some pair together. So we could say that there exists an a and that there also exists a b. So there exists a and z. There exists b and z. So just some pair exists such that x equals a divided by b. Alright? So we could also put something down there about b not equaling 0. Although if b did equal 0, then this whole statement would be false anyway. And so we wouldn't really have to worry about it very much. Alright? So if we look at what happens here, so if x is a rational number, then there exists some number a that can be paired with some number b such that x is equal to a divided by b. Alright? It doesn't have to be unique. For instance, say that we had that x is equal to 3 over 5. You could have that a equals 3 and b equals 5. That's the simplest way. But you could also have that a equals 6 and b equals 10, or that a equals negative 9 and b equals negative 15. Alright? So remember, when we just say there exists, that just means that there's at least one. There's at least one number a that can be paired with at least one number which we call b, or at least one integer a that can be paired with at least one integer b, such that x is a divided by b. And so it could be that A is 3 and B is 5, or that A is 6 and B is 10. The choices don't necessarily have to be unique. All right? And so if X is rational, it just says that some such combination exists. And if we look in the other direction, if some such combination exists, then that means that X has to be rational. So say some combination of integers A and B exists such that X is A over B. Maybe A is 25 and B is 7. Well, then X is 25 over 7 and X is rational. All right? So again, the if and it's an if and only if, it goes back and forth. All right? So one last one that we will deal with is the idea of a prime number. So this one gets a little bit more complicated because there's multiple criteria that we're going to be using. So when we talk about prime numbers, for every real number, do we say that it's prime or not prime? Like, would you say that 20, like if you're talking about prime numbers, would you even consider something like 27.8?
I think we just talk about maybe even natural numbers.
Yeah, we really just talk about the natural numbers, all right, when we're talking about whether something's prime or composite. All right, and so we'll start with X is prime. All right, and so we got to decide for any natural number, we got to have some condition to decide whether or not it's a prime number. So what characteristics do prime numbers have?
Their only factors are 1 and itself.
All right, so a prime number, the only factors are 1 and itself. However, while that is a necessary condition of being a prime number, it's actually not a sufficient condition of being a prime number. There is a prime number there's a number who isn't prime and yet satisfies those conditions that its only divisors are 1 and itself.
That would be 1?
Yeah, that would be 1, where 1 and itself are the same thing. And so when we define a prime number as a mathematician, you actually have to specify an extra condition simply that X cannot be equal to 1. All right, so let's look at the conditions to be prime. All right, so conditions of prime numbers. All right, so cannot be equal to 1. And the only divisors we'll just call, say you have a prime number that's called X, it cannot equal 1, and only divisors are 1 and X. All right. So we need to sort of put together some way of working with this. And so we need to somehow specify, so we have these divisors, and we can make a proposition that just talks about like y is a divisor of x. So since you could have a statement like dxy would be y, or I guess you'd want to have it yx because of the order, or you could have dyx dy divides x. Okay, and so we want to say that if y divides x, if y divides x, what would have to be true about y?
That y is either 1 or x.
Yep. Then y equals 1 or y equals x. All right? And this is a condition that's true for every number y. All right? So if I give you some natural number y, so either y doesn't divide x, in which case the if-then statement is vacuously true, or it's possible that y does divide x, but if y divides x, then we can conclude that either y is equal to 1 or that y is equal to x itself. All right, so let's look at here. So x is prime if and only if. There's a bit of stuff here. So the first thing is that x can't equal 1. And, actually we'll use the ampersand. That's what we've typically been using for our ands, because both of these conditions have to be true at the same time. And for all y, if y divides x, then will we have this or statement, and then we gotta close that parenthesis, and then we gotta close this parenthesis here, and then we gotta close this bracket. So there's a lot of statements sort of nested within themselves in this case. But let's sort of look at this. If x is prime, then x is not equal to 1. And I didn't specify where y comes from. All right. Then both x can't be equal to 1. And for every natural number y, if y were to divide x, not all y's divide x, but if they do, then they have to either be 1 or the number itself. And so this is a nice way of saying that everything that divides x is either 1 or x itself. Because if it divides x, then it's either 1 or x. All right? And so we have an and because both of these conditions have to be met simultaneously. We have an or here because there's two different values that y could be under the assumption that y divides x.
Okay, can you fix the smeared y?
Oh, yes.
It's hard to read.
All right.
Thank you.
And so I think that we'll cut the video right here, just because if the video goes too long, it's going to have too long of upload times. All right, so I hope that this lesson was helpful in getting you guys to be able to think more about how nested quantifiers work.